So how do we solve a problem in which we actually have different types of motion? Here's the example. A car starts from rest and accelerates for 12 seconds at a constant rate of 1.5 meters per second squared. It then travels at a constant velocity for 25 seconds. How far does the car travel? We'll be using our equations 1, 2, and 3 for motion with a constant acceleration. But we recognize that we actually have two stages here in the motion of the car. Stage 1 corresponds to the accelerating stage, for which we have acceleration of 1.5 meters per second squared. We have initial velocity 0 because the car starts at rest during that stage, and it lasts for 12 seconds. The displacement here, delta x, or in other words x minus x naught, will come from equation 2. I will move x naught to the left hand side so I can see that displacement will be equal to v naught t plus 1/2 at squared. Or numerically, I will have 0 for the initial velocity, so the first term here on the right hand side will be 0, and then I have to add only the second term, the acceleration term, 1/2 of 1.5 meters per second squared times 12 seconds squared. So I find out here that the displacement during the accelerating stage is going to be 108 meters. Now, the second stage is a motion that with a constant velocity, or a coasting at the constant velocity. It is still a motion with a constant acceleration. It's just the acceleration is 0. So we can still use equations 1, 2, and 3. Do we know the velocity with which the car is coasting during that stage? The answer is yes, because the stage 2 begins where the stage 1 ends. In other words, the velocity during stage 2 is going to be the velocity at the end of stage 1, or what we will normally call final velocity for stage 1. So if we go back to stage 1 and figure out what the ending or final velocity at that stage was of the car, we will know at what velocity it's coasting during the second stage. Let's use equation 1 here. V is equal to V naught plus AT to figure out what is the velocity of the car at the end of stage 1, or at the end of those 12 seconds during which the car accelerated. Once again, V naught here is 0 because the stage 1 started at rest, and then I have to just add 1.5 meters per second squared, which is the acceleration of the car, times the 12 seconds, the time that stage lasted. So I see here that the velocity at the end of stage 1 is going to be 18 meters per second, and that will be the velocity for the coasting during the stage 2. If I want to find the displacement at the stage 2, I have to go back to equation 2 again. X minus x naught will be equal to v naught t plus 1/2 at squared, and apply it for stage 2. Here, the initial velocity at the beginning of stage 2 is going to be 18 meters per second. That is the ending velocity from the previous stage, multiplied by the time, 25 seconds. The second term here is going to be 0 because during stage 2 motion we have no acceleration. So once you put when you put 0 for A, we end up here that the displacement is going to be 450 meters. What is left here is just to add the two displacement. The total displacement will be equal to the displacement during the stage 1 of 108 meters plus 450 meters the displacement during stage 2. So the total displacement is going to be 558 meters.